Hello, and welcome to the presentation on a methodology for successful university graduate CubeSat programs. My name is Aaron Abwoff, and that's me talking to you. Just this past May, I completed my master's degree at the University of Colorado, and I've been involved with the graduate CubeSat programs at the University of Colorado for the past 4 years. This presentation is going to cover just the highlights of our paper, which is informed by more than a decade of CubeSat development at the graduate student level, spanning 4 successfully operated missions, 2 expected to fly in the next 18 months, and 4 more missions expected to fly in the coming decade. Many of the examples in this paper reflect our strategy towards building a successful CubeSat program and are taken from one of our current missions, the Maxwell mission, which is expected to launch in the fall of 2021. The Maxwell mission is developed, tested, and integrated in 2 labs at the University of Colorado, the 443 lab and the STIG lab. That's the Satellite Technology Integration Laboratory. The Maxwell program has been lucky enough to take advantage of the previous decade of experience on CubeSat programs and lessons learned from previous missions, which makes it a great example to illustrate some of the strategies for making a CubeSat program efficient and successful at the graduate student level. We divided the paper up into 3 major sections, first of which briefly covers the major items that need to be put in place to set up a CubeSat program with the best chance of success. Basically setting forth what we think are the most important things to have in place to start out so that the program has the greatest chance of success down the line. At the top of the list is having a project sponsor, which provides the funding and some external accountability for the program. For the Maxwell mission, this sponsors the University Nanosatellite program, but this can really be any source of funding with some kind of external accountability that requires concrete deliverables from the students. Then it is important to create a baseline program to reliably recruit and retain personnel to work on the mission. The University of Colorado uses the Graduate Projects course as the primary way to recruit students to work 2 semesters on a number of CubeSat programs. Each program also provides additional flexible opportunities for interdisciplinary students to also get involved and for highly motivated students to take part and stay on those programs longer. Finally, thought must be given to balancing programmatic parts of the program with the push to accomplish technical work. There is necessary red tape in order to keep a program running smoothly in the long term. Establishing a strategy towards efficient meetings both within and across subsystems will improve communication and task tracking, as well as planning to make consistent progress. We have found that official document tracking is also a huge bonus for managing student turnover and preventing the loss of knowledge between generations of students, because having this official track documentation forces important information to be recognized and then tracked, which helps for the long-term success of the project. There are also details about how we implemented these concepts in the paper, as well as some specific examples of how they are applied on the Maxwell mission. We will then move into program infrastructure, which deals with everything that needs to be put in place on a program such that it facilitates short-term and long-term success as well as continuity. These are the non-technical parts of the program that we have found are critical for mission success. We'll begin by touching on the leadership and recruitment. On a student project, it is up to the student leadership to institute, manage, and enforce the policies and procedures for keeping the project moving forward in an efficient and organized fashion. Included in this is also the ability to evaluate current policies and procedures and to iterate on them so that they are adaptable to the team needs as the project progresses forward. For long-term success on the project leadership side, For long-term success on the leadership side of the project, it is critical to identify strong students for top-level leadership positions. On the right is the Maxwell project leadership structure. For the project manager and systems engineering positions, having students for longer periods of time, typically longer than just a single year, is a great boost to team organization and continuity for both technical and programmatic information. You can also see the spot for the deputy project manager. We found that having this position is a great way to train up the next generation of project manager so that the seamless management transition happens across student generations. We also have seen that explicit recognition of stellar work sets a good example and incentivizes all the students on the team to continue to work at a high level or to put in a little extra work in order to get recognized. Knowing that leadership is paying attention to the technical work being accomplished is a powerful motivator on a student-run project. Keeping the team fully staffed is an ongoing challenge. We have found on Maxwell that getting the word out about the program both within the aerospace department and to other departments like electrical engineering and computer science can bring in a lot of additional interested students. It is especially important to spread out the word about the project because oftentimes students hear from other disciplines like electrical engineering have valuable skills that help push development forward. Training is also especially an important facet of keeping the project on track. As new students join the project, making sure knowledge can be transitioned forward to the new generation is a critical task. Our training approach involves every semester, and our training procedure evolves every semester, and this flexibility allows us to improve the rate at which new students become familiar enough with the system so that they can identify and complete tasks needed to move it forward. The training begins with a high-level overview of the system, which can come from sources like a comprehensive mission handbook or a top-level system block diagram like this one. You can see here that all the components of the system, how they're connected together, how they communicate with one another, and how they are all powered. When we move into smaller groups to work with the systems engineer to learn more about the specific hardware in the lab. And finally, once students have figured out which subsystem they're most interested in working on, they then do a deep dive with the responsible engineer for that subsystem. And finally, training leads us to the importance of knowledge transfer on the project. We have improved the knowledge transfer on the Maxwell mission over the years by tracking official documentation on technical work, continuing a regular review schedule each semester to align thoughts and designs across subsystems, and by making sure department members leave a list of specific, and to make sure that departing members leave a list of specific tasks for new members to get started with. Team communication is also critical. This is the shortest section of the paper, but one of the most important. The essential goal here is to facilitate the transfer of relevant information quickly to the right people. Students always have different schedules, so regular meetings or office hours can be tricky to coordinate. Instead, we've seen a lot of success on our programs with instant messaging platforms like Slack, which allows students to easily share links, files, data, and information. Don't forget to also keep the PI and the project advisors involved in the student communication channels. So have them on the Slack, just like you'd have any other student working on the project. Having these people available to answer questions and offer comments on discussions happening between students can be an invaluable way to make development better from the get-go, instead of learning in a review that design choices made are not going to be suitable. Plus, these folks have great experience, which is also an invaluable resource for students learning how to build a CubeSat. We also heavily encourage students to ask questions about the mission or what they're doing in public channels, so that everyone on the team can benefit from the discussion when reading through or helping others answer those questions. CubeSat projects are highly collaborative efforts, and getting more people involved in a discussion leads to more diversity in ideas and a greater chance for a creative and exceptional solution. We'll then move into project infrastructure, which covers some of the more tangible technical aspects of CubeSat programs. For the project lifecycle, there are a few ideas that we have found to be extremely useful for the program's success long term. As with all missions, your program will undoubtedly have the traditional PDR, CDR, TRR, and PSR cycle, which you can see here in the Maxwell milestone schedule. You'll also notice that there are a lot of other reviews surrounding the traditional milestones. These other reviews are additional reviews that help align the different subsystems along the way so that students continue to make sure that everything they are working on is still compatible as a system. We also want to stress the importance of having regular interviews as well, not just with the sponsor. Each semester, we will include a mid-semester technical interchange meeting, which allows the subsystems to go into details about what they're working on, also giving everyone else some additional insights on what others are doing. The end of the semester is also reserved for either a milestone review or an internal end of semester review. The most important part of the reviews at the end of semester is that they force all of the subsystem teams to communicate with one another to make sure that the design is still all on the same page. The second important feature of these semester reviews is that they put together a list of specific tasks that need to be accomplished to keep making progress on each subsystem. It's this task list that makes its way into a burn down list for the mission and gives us a starting point for which new subsystem team members can build their task waterfalls for the upcoming semester. Let's now talk briefly about hardware. Some of the major lessons learned that we've seen over the years and seen success in implementing policies to cover are specific to the custom designed circuit boards that are used on our CubeSat missions. Just from a hardware management standpoint, we have started assigning each printed circuit board, or PCB, a unique serial number and tracking it. This means its location, its status, notes on any modifications like white wires are all tracked in a central location. We also store all of the source files for the boards in Git so that each rev of the PCB is saved, and we can keep common part libraries between all our boards. We have also been pleased by implementing a functional and acceptance testing on all of our PCBs. This process is specific to each board, and it does a basic functional acceptance test to ensure that the board was manufactured and populated properly so that we know it's in working order. This is all a very useful test to determine if hardware is still, this is also a very useful test to determine if hardware is still acceptable for use following testing anomalies that had potential to damage it. We cannot express the importance of block diagrams as well. On the right is the block diagram for the ADCS subsystem on the Maxwell CubeSat. If you could zoom in on it, you'd be able to see that all of the sensors, actuators, processors, power connections, communication buses, and sensor configuration information is listed there, making it a very useful diagram for both hardware and software development on the ADCS side. This brings us into software. One of the most important things we mentioned regarding software are fairly straightforward, but without them, software can become a very tangled mess that's difficult to gain confidence in. I want to stress the importance of having a robust version control system for all the software and the related files. Having periodic software releases that have detailed update notes is extremely helpful for tracking the progress of the code you're writing as well. The other major facet when it comes to a series, is to come up with a series of approved code release criteria. This could cover formatting, documentation for whatever was written, and most importantly, some kind of basic functional or unit testing that you can run in an automated fashion to determine if the changes you have made have affected something else in the code unintentionally. Software is also greatly benefited from incremental testing. As soon as you add one feature, you should test it to make sure that it works. This makes the debugging process a whole lot easier because you're only debugging one addition instead of many. It also helps develop confidence in the robustness of the code because having incremental testing procedures set up for the code allows functionality to be added each time to the release criteria. Thus, any features added down the line continue to test features introduced earlier. Finally, when testing is performed with the software, the version of the software should always be noted in the procedure and the results so that the exact test scenario can be replicated if the need arises. This can be as simple as noting the git commit at the code, since it's completely unique, which makes adding this step to any procedure a very low effort and high reward action. So those are the highlights from our paper. We encourage you to read more in depth to gain some additional insight from our experience over the past decade of missions. If you have any additional questions or comments, please reach out and let us know. We'd love to hear from you. Thank you.